Okay, good afternoon. So, not much on the agenda today except for answering the questions students had about the quizzes. So, several students, not just one or two across, like several students across both across both of my sections had lots of questions about the sequential problems. So, let's address that. Okay. First thing everyone should know is, well, actually, let me bring it up first. So, quizzes and all right. All right, this was quiz 7 and quiz 8. I'm guessing everybody was fine with 1, 2, and 4, right? At least that's what it seems from the student responses. And then we had okay. So sequential, first thing you should know is not gonna be on the final exam. Okay. It's that's one of the reasons I gave that in quiz 8 in the last week of class is because I've already assessed it, and then I don't plan on including it in the final exam. So sequential logic is not going to be on the final exam. All right, and we'll talk about the final exam after I get done with this. So one of the reasons also that you see here that it's not a big chunk of the quiz, it's 5 points, is because these two were mostly designed to assess students' thinking, students' thought process. Okay, it's technically like a successful implementation of the logic is not possible within the realms of EE 321. Okay, let me put it that way. An EE student would have to take like an entire academic year of digital logic design to actually implement this. Right. So it's a low level overview that we are doing in this question. So if I was to implement this, which is basically to implement the above function with gates, right? CF and CE and 8F. Let's create an empty space in our in our class notebook. And let's see, since we were in chapter 4, let's go to the end of chapter 4 and add a page and talk about quiz 7. And the question was, consider the hex number CE8F and then implement it. So let's paste it here. Okay, so we have two numbers, CE and 8F. I think most students got that correct. Most students also got the theoretical complement, 1's complement, 2's complement correct. So everybody is good on that. So let me ask you, if you have two hex numbers, if you have a hex number and it's 2 digits, how many bits of data do you need to describe that number? 8, right? I think everybody got that correct too.
What?
That's 8.
Can't hear you.
Okay. So we have 8 bits. Now, CE, 8F, AA, FF, 88, doesn't really matter what that number is, but the number can be represented in binary, either by 0 or 1, right? So if it's 8, it would be 1000. You need 4 wires to describe each digit. So you have 8 wires. How do you get the 1's complement? Not gate, right? you'd simply take the wire, you'd have an array of NOT gates. And that would give you your ones complement. Right? So this is the hex number. Here's the hex number. Now you got 4 bits, 4 wires, could be 0, 0, 0, 0 or 1, 1, 1, 1. But if you pass it through a NOT gate, it gives you the ones complement. So far, so good. I think everybody pretty much had this correct too. Now, you want to create a 2's complement. What do we need if you're doing 2's complement? I think everybody got the theory correct on this one too. Add 1 to the last digit. So let's say this was the MSB on the left. This is the LSB. We simply add a 1. What do we need for adding? What kind of gate do we need to add? OR gate. If you want to add a 1, what do we do to this pin? Plus 5 volts or plus 3.3. Let's use plus 5 volts, which is something that each and every one of you did in the lab. So when you created those circuits, there were many pins in those logic circuits that were connected to either plus 5 or they were connected to ground. If they're connected to plus 5, you're permanently, for the purposes of that circuit, you are connecting that to logic high, meaning 1. You're supplying 1 into that circuit. If you connect it to ground, you're supplying 0 to that circuit. Right? So if a pin is connected to plus 5 volts, you're supplying 1. So the last digit, you add 1 to it. And then you have the results. What do you do with the results? We have to, well, AND gate, but what is the, how do we subtract using 2's complement? We add it to the original number, right? So the original number is here. All we do is pull wires down. Right? And then we add the outputs to an OR gate. I'm not going to draw all of them, otherwise it's going to get really messy. But right, so here is the ones complement. Here is the 2's complement. And here would be the subtraction, or logical subtraction. Yes. So it's a very valid question. So I want to say this is not a trick, again, because I simply wanted to see what students would implement. Okay. The actual circuit would be very different because you illustrate that problem. What do we do with all those bits? So here, let me ask you this. What, not you, but everyone. If you're adding decimal 1 plus 1, what do you get? 2. If you're binary, what is 1? A 2-digit 1 in binary is 0 and 1. So if you add 0 and 1 and 0 and 1 in binary, what should you get? Right? So you remember, there was a question being asked, if we add 1 plus 1, we get a 0. How do we get a 0? Right? So 1 plus 1 is a 0. And then there's a carry bit. So this would be the sum. And this would be the carry bit. So we design a circuit to incorporate that carry bit. And the reason some students asked about the XOR gate while the quiz was going on, because I'm guessing that they searched online and they found the circuit. So if you all, I don't know if it was this section or the other section, but as soon as the student asked, I was like grinning on my face. It's basically they looked it up online. But this again, this problem was not, it wasn't, I'm not looking for something like, okay, students should get 100%. It's not fair because this is not something, we do for E321. But as part of the larger question, I just wanted to see what students would do and, do about it. So we'd have a circuit for a 1-bit circuit. You'd have it created with like 4 gates. We'd incorporate an XOR and or there are many ways to do that, but we'd incorporate where you'd have 2 outputs. You'd have a sum output and you'd have a carry output. It's known as a 1-bit adder circuit. Okay, and you'd have 8 on how many bits you want. If it's a 64-bit system, you need a 64-bit adder circuit. Okay, but it takes the carry and carries it over to the next digit, which is what is not shown here. Yes. Well, this is just to show if you just apply the logic that we learned in the class. I mean, it wouldn't really work out that way. Because the output of this bit needs to go to the left. Because theory, when you did the theory, everyone pretty much got it correct. So if you have in the theoretical calculation, I can't remember, but 0, 1, 1, 0 and 0, 1, 1, 1, and then you add a 1 to it, then every subsequent digit is carried forward to the left. And so the logic gate implementation does not have a carry implementation. So it was technically not possible to do it with the information to do it. Okay. Hence, it's only 5 points. So in the quiz grading, there's not, there's no penalty on it. Everybody gets the 5 points. Okay. But it was fun to see, the responses. And pretty much everybody else got the combination logic correct. But it's not as a way of like torturing students or having fun at students' expense. This is just to make you think on how actually it's implemented, right? Rather than me just, providing something in, which is pretty much how all lectures are based on. But I thought it was a good way to incorporate that question in here because you're already doing 1's complement and 2's complement. And then what would it take to actually implement it in real life? Anyway, that's what that was. And then the other one was also kind of similar to that, which was quiz 8. So let's see, quiz 8 was, and again, this is part of sequential logic. So that's also not something that I'm going to assess again, right? So in here, the circuit can be, what do you think it can be? All of them, absolutely. And I stated this in class. We could have parallel inputs, parallel outputs, right? All you got to do is take Q0 to Q3 out in parallel. You might need to add a few more gates perhaps to control the output. But if you take all the outputs at the same time, that's parallel output. So there's serial in, serial out, there's parallel in, parallel out, and then other 2 combinations also. So it can be function like all of them. Right? That's the right answer. And then clear is 0, output is, so you got to look at the bubble. So if it's clear or preset or enable, then you have to look for the presence or absence of a bubble. If there's a bubble anywhere in here near the clock or the clear, then the bubble requires an active 0, meaning it requires a 0. If there's no bubble, it requires a 1. So when clear is 1, output is cleared at 0. And when clear is 0, output just stays its previous state. That's it. And then enable is 0. output stays previous state. When enable is 1, output is equal to the input. Again, concept questions, everybody has different words, but as long as the meaning is conveyed, then you get full points. All right, timing diagram. So assuming enable is active, there are a couple of different ways to display the timing diagram. So let's talk about that. All right, I'm gonna have to move this to the side. Actually, it'll work. Okay, so clock for 10 cycles, 50% duty cycle. So it doesn't matter what you draw out as long as it has 50% duty cycle. All right, so CLK. That's not quite 50%, but you get the idea. So that will be the clock, right? And the circuit was all active high. I mean, there was no bubble anywhere, and it's edge triggered. So it'd be positive edge triggered. Okay, positive edge trigger. Now we want to convey A, B, C, D. And we said parallel, the enable is active high, means connected to 1. So whatever input comes in is going to go move at every clock cycle. If you're giving in parallel, if you assume serial output, it's going to shift 1 by 1. If you assume parallel output, then it just shifts down in parallel. So if enable is 1, as the problem statement suggests, you can make an assumption whether you're describing the timing diagram for serial output or parallel output. If you do parallel output, it's easy or easier versus serial output. Okay, serial output is going bit by bit. So for every clock cycle, it shifts down. For parallel outputs, whatever input you give in, you're going to give at the output. So if it's A, B, C, D, let's just do this. That's a clock, and I'm going to do A, B, C, D separately. One goes, so the first set of data goes first, right? Parallel in. Then followed by the second one, and then the third one. If you think back to E201, if this is the x-axis and time, 0 is somewhere here. 0 is basically the time we begin analysis. In this case, the time where we apply our input signal. So this is the future. In that sense, this would be the past, right? But here, if I wanted to say that I am sending in the input from the left, then there are two ways to describe this. You can draw A, B, C, D completely separate for all three of them. Makes it very long and lengthy. But if you want to describe it all at once, you can do it this way. Start with the third one. Third one is 0, 0, 0, 1. So I would say A is 0, 0, 1. B is 0. C is 0. And D is 1. How long it lasts? Assumption. Doesn't really matter how long it lasts. It could be half a clock cycle, could be a longer clock cycle, doesn't really matter. Okay, it's not provided. Again, students can think and determine how long they want to. If you want to make it equal to the clock cycle, that's also fine. I think that's what several students did. The 0, 0, 0, 1, that's a third one. But preceding that should be an input of 0, 1, 1, 0. So 0, 1, 1, 0. So A stays at 0. B goes to 1. C goes to 1. And D goes to 0. And again, how long they stay at that particular state is up to the circuit designer. And then finally, we have 1, 0, 1, 1. So A goes to 1. We don't know what happens to A after that. And then B goes to 0. C stays at 1. And D goes to 1. And this is fed as input into the system. Again, the width of this could be exactly the same as the clock pulse, could be shorter than the clock pulse, so that when it arrives, the input simply moves to the output. Yes. So in this case, since I'm going from left to right, I just want to show going from left to right. If I wanted to show going from right to left, we would just simply start from the left. Okay. If I was going to show input going in this way, then I would flip everything. So the question being asked is, how would it look for what? So preset or enable. Enable is high, meaning whatever we send as input to ABCD is going to go to preset.
But wouldn't we want it off after we have input the data so that it doesn't continue to?
That's not specified. That's a very good question. Do we want the enable to switch between 1 and 0? Good thinking, yes. So again, do we want the enable to go to 0? Depends on the application. If you want just a continuous stream going in, you might just keep it connected to high. So let's say we are sending, for example, if you're sending a file to print via USB. Well, USB or parallel port doesn't really matter. But then we want the enable pin to be high as long as the data is being sent. We don't want it to like shut off in the middle. It's a continuous stream. The clock signal keeps everything synchronized. So it's parallel. All of the bits come in, and then it go out, and the next one comes in, goes out. Next one comes in, goes out. And that would be it. Obviously, this is a very short and simplistic explanation. But if you really wanted to design something like this, then we'd have a lot more associated with it. Okay. Again, these two were kind of designed to make students think a bit. So even in this case, there's not going to be too much penalty for students. But the fundamentals, of course, we'd expect the students to understand the fundamentals. All right. Okay, let's talk about the final exam. We have about 25 minutes left, so there's a few things. Final exam is here. Let's bring it up. So final exam has been displayed since the first day of class. Right up the top, I said, please read everything on this page, right? Final exam is mandatory. It's not optional. Optional in the sense you could choose to skip it if you don't wish for 25% of your grade, right? The exam counts for 25% of your overall grade. So if you wish to not take the exam, that's your choice. But I don't drop it. It's not optional at my end. Okay. So right away, your grade would drop by 25%. Okay. All right, there is no Zoom option. All final exams are in person in this classroom. Our regular time for the final exam, according to Cal Poly schedule, is on the Monday, first Monday of finals week. I mean, actually, not first Monday, the Monday of finals week. 17th from 10 to 1. Okay, again, these have been here on the first day of class. So yeah, Monday. If you don't want to take it on the Monday, you have two other options. You can take it on a Wednesday with the other section or on a Friday with my other class, right? Both of them are in this classroom. So again, the university scheduled final exam dates and times always take place in the same classroom where you took the class, the official classroom. The university scheduling, classroom scheduling committee decides this, which courses take place in which classroom. And then the schedule for the final exam is also decided by them, so that that way there is no clash, right? That means the room is available during the course time. All right, so same classroom as a regular lecture room. And then if you also want, there's an alternative option, is taking it on Saturday before finals week, which is this coming Saturday. And this coming Saturday. And this coming Saturday, that classroom, more likely than not, will be either 2131 or 2126 across the hall. But it's in building 20, not in this building. It's in building 20. So if you do wish to come on a Saturday, please go in person and check out where those rooms are. Okay. All right. So there's a form, survey form, that you need to submit if you wish to take it at an alternative time. All you need to let me know is when you wish to take it. If you wish to take it at your regular time on a Monday, you do not need to submit this form. Okay. Only submit it if you wish to take during an alternative time. That's all. If you take it on a Saturday, your request is approved, pretty much. You don't need to know whether you can. I will accept requests until Friday afternoon. Okay, I just need to know enough in advance so I can print those exams in time. All right. So if you let me know by Friday afternoon, perhaps even like till 2 or 3 p.m., I can have enough time to print out enough exams for the Saturday. If you wish to take it on the Wednesday or Friday, I will have a note at the top of this page that I will constantly update somewhere over here. At the top right here. And it will have a date and a time note on it saying that all requests approved for, all requests received before this date and time are approved. Okay, so if you requested like a Wednesday today, by tomorrow I will have and saying, okay, all requests by Thursday 8 a.m. are approved. And I'll update that as the days goes along. The reason is some students from the Wednesday and Friday finals will take it on a Saturday. Some may decide to take it on a Monday. So whoever decides to take it on Saturday empties up a seat on Monday, Wednesday, and Friday. So depending on how many students take it on a Saturday, I'll have empty spots. There's only about 40 chairs in this classroom, so we cannot exceed that number. Fire safety codes. Okay, so we cannot exceed that number. Pretty much, I've never had any issues with students taking the exam on alternative dates, and I don't foresee there will be any issue. Okay, so pretty much all requests for alternative times will be approved. It's open book, open notes, open internet, but open internet is only restricted to course material. You cannot access, you cannot like go online and find how to create a 4-bit adder. Not that I'm going to ask you, but again, access is limited only to course material. So you can use your laptops, you can use your tablets, but only to access course material, meaning slides, PDFs, textbook, and online homeworks. Okay, so internet is only restricted to that. I will be at the back of the classroom, so I usually sit in the middle at the back of the classroom, as obviously I cannot monitor everybody's laptop or tablet from the front. But you can have your laptops, you can have your tablets. Make sure you bring your chargers or fully charged laptop. There are PowerPoints all at the back row. There are some in the periphery. I might move some of the desks closer to the power outlets, so everybody has enough space if they want to do that. All right, but make sure you charge everything and bring. Let's see. Yeah, that's that. Let's review the material. So oh, before I do that, let's see. Should have something here. All right. So I had one problem for diodes or rectifier circuits, meaning for different diode models, some analysis. One problem on Zener diodes, more likely than not be a Zener voltage regulator problem. Okay, Zener voltage regulator problem. Diodes and rectifiers, perhaps load line analysis, ideal diodes or rectifier circuits. Okay, and I'll go over into the notebook and I'll point out. BJTs, again, fundamental conceptual questions, types of regions of operation, types of BJTs, how a PN junction diode works, how a BJT works, analysis and biasing, and load line analysis of amplifiers. Okay, kind of the problems that we have seen in the class and in the homework. Op-amp circuits, one problem similar to what we have seen in the class or the homework, and fundamental concepts. Logic circuits, only up to combinational logic circuits, meaning binary numbers, hex numbers, theoretical calculations, and implementation of certain logic, similar to what we did in the class and on the quizzes, and no sequential logic. Okay, no sequential logic. All right. So diodes. Diodes had some fundamentals about semiconductors, semiconductor device physics. We had circuit analysis. We did a little bit of circuit analysis. I'm not going to assess that separately, but again, everyone should be aware of how to do basic circuit analysis at this point. So how are P and N type semiconductors created? So, short conceptual questions, short answer questions based on those. PN junction, what it does in forward bias and reverse bias. Now IV characteristics, load line analysis. So we should be familiar with load line analysis. Ideal diode model, we did several examples. We did homework problems, and we also did couple of examples in last week. Basically, okay. So basically, in ideal diode analysis, we make an assumption whether if the diode is on or off, right? So we make that assumption based on the circuit conditions. If the anode is higher than the cathode, diode is forward bias, hence it's on. You replace it with a short circuit. If the anode is lower than the cathode, diode is off, reverse bias, open circuit. So you replace based on your assumptions. Then you do your calculations and you check. If your assumption is that the diode is on, the diode voltage must be positive. Okay. So in real diodes, sorry, not diode voltage positive. Ideal diode, it should be 0 because it's a short circuit. In a constant voltage drop model, it must be 0.6 or 0.7 volts. And ID must be positive. Okay. If it's a short circuit, VD would be equal to 0. Okay. And ID must be positive. If VD turns out to be negative or ID turns out to be 0 or negative, then the diode is not forward bias, it's off. Or reverse bias. Then your assumption is incorrect. You go back and redo your assumptions. Okay. If you assume that your diode is off, then your VD must be less than 0, must be negative, and current should be 0. It's an open circuit, no current would flow. Okay, no current would flow. So that's the ideal diode model. Then we had multiple diode circuits. So again, we made assumptions. So go over this problem, go over the homework problems, also the problem that one of the homework problems I solved in class, the one with the diamond. Okay, so please make sure you do that. The offset diode model, this is also known as the constant voltage drop model. It's basically diode requires a certain amount of voltage to turn on. So we say it's either 0.6 or 0.7. It will be stated in the problem. So ideal diode and this offset diode model are exactly the same. In reverse bias, it's off. Voltage is either negative or zero. I mean, voltage is negative and current is zero. In forward bias, it's a short circuit with a voltage source. So voltage source, here we say 0.6 volts. In the problem, I would state either 0.6 or 0.7. If it's not given, assume whatever you want. But it's a voltage source of 0.6 or 0.7 volts. Okay. So ideal diode and this offset voltage, offset diode model is exactly the same. No difference, except in forward bias, you have a voltage source. All right, then we have the Shockley equation, terminology, diode rectifier circuits. Please review these few slides on how diode rectifiers would work. Okay. And again, any problems that I asked here will be from the homework or the quizzes. Then we have the Zener diode problems. Voltage regulator, again, as I said, Zener diode, most likely 99% you will see a voltage regulator problem. Okay. Load line analysis. So I won't do Zener load line analysis. But again, it's similar to the diode load line analysis. So no Zener load line analysis. New voltage regulator. Zener regulator will load. Okay. So make sure you review this. Then we had diode clippers. And then combination circuits using diodes, Zener diodes and regular diodes. So make sure you go through, again, review how the clipper circuits work. Clipper circuits or any kind of diode circuits can be analyzed using the ideal diode model. And that's what we used here. Okay. We used the ideal diode model to analyze the circuit. So if you practice the ideal diode model, you should be able to do the offset diode model. You should be able to analyze the diode rectifier circuits, and you should also be able to analyze these kind of clipping circuits based on that ideal diode model. So make sure you understand that thoroughly. Okay, that's the most important. We won't do diode clampers. No clamping circuits. Okay, no clamping circuits. And that would be it for chapter 1. I got about 10 minutes left. BJT, again, short answer question based on fundamentals and concepts. You should know what it means and how the three regions, base collector emitter, and how it functions, basic operation, BJT parameters, alpha, beta, how it can be used as a switch or as an amplifier, the characteristics, modes of operation, active, cutoff, and saturation, and then how to determine the mode of operation. So operating modes, basically here. Okay. And then we had examples for determining the operating mode. We had the load line analysis. So I might ask something about the load line analysis. Problem could be from here. So please make sure you review this problem. Anything we do with the NPN examples is applied equally to PNP, except holes are switched for electrons and vice versa. Voltage polarities are flipped and current directions are reversed. Okay. In an NPN transistor, current comes out or flows down in the emitter, out of the emitter. Hence, the arrow points outwards. In a PNP, the current flows into the emitter, hence the arrow points inwards. So again, it's just reversed. Voltage polarities are reversed. VBE in an NPN transistor is 0.7. In a PNP, it would be VEB. So VBE in a PNP would be minus 0.7. Or VEB is 0.7 plus 0.7, right? Same voltage, we just flipping because of holes and electrons. That's all. So load line analysis. Make sure you go through this entire example. And then 4 resistor bias circuits. All right, so we won't do this. Not 4 resistor bias circuits. Not separately. Okay, not separately. So I won't assess. Okay, BJT. That's it for BJT. Then we have op amps. Op amps is basically, we'll stick with what we did in class and what was there in the homework and the quiz, and that's it. Okay, you'll see something similar. Short answer questions, fundamentals. Summing amplifier, non-inverting amplifier. Filters. Okay, no filters. Not many filters, okay? Just use as a standard inverting or non-inverting amplifier configuration. That's it. No filters. And then chapter 4, we already went over the basics, the fundamentals, binary number system, Boolean algebra, mathematical operations, logic gates, and combinational logic using the gates. No flip-flops, no sequential logic, nothing like that. Okay. Binary numbers, hexadecimal numbers, all of that. Conversion of binary to decimal, decimal to binary, hex to binary, hex, vice versa. And then gates, and that's it. Up to here. Yes. No sequential logic. If you want, you want. So, no timing diagrams. Yes. Quiz questions I asked. So they are there in the solutions. I think should be right there. It's already there. Yeah. I need to do 6, 7, and 8, but they're there. Okay. It's been part of the notebook. Okay, see a lot of surprise on a lot of students' faces. How many of you were aware of this? Or okay, 2 out of 20. Yeah, yes, Samantha, you had a question. No flip-flops. I mean, students can wear flip-flops and come to class, it's fine, but I'm not going to assess on those. All right, 4 minutes left. Yes. You mean during the final exam? That's a good question. Nobody's asked that before. So question being asked is if they could access the lecture videos during the final exam. I guess technically it counts as course material since I'm incorporating it in the course. So yeah, my answer would have to be yes. You can access it if you want. please ensure you bring a pair of headphones. So yeah, you can access lecture videos if you want. Yes. Yeah. I mean, if you have PDFs, you can access the PDFs also, it's fine, but nothing outside of class material. No asking for help, no looking up the internet. I mean, as I said, there are online calculators. So if it's like problems you won't be able to solve directly because it's not on the web, so you can't find it. And I don't want to see anybody typing anything also about, about the exam. But there are online calculators, for instance, binary to decimal, decimal to binary, hex to binary. So students might say, okay, let me just verify whether my answer is correct or not. Okay, so there's an example of a use case scenario. So that's not something I want students to do. Okay. So you have access to the course material, you have everything. You don't need to worry about if you just want to do equation sheets on your own, that's fine. It's up to you. You have everything available to you as with regards to course material. But show me your best work. Kind of thing. No class on Friday. I'll be in my office. Students answer questions. If you want, stop by anytime. And one final thing is the course evaluations are open. As a reminder, this is not here. Let me bring it here. So as a reminder, every student in the class receives extra credit for a little bit of extra work. So right now the response rate for this section is 9 of 35. So approximately 1/4, right? 9 4s are 36. Yeah. Right. So every student in the class, so it's a 25% response rate. So every student in the class receives 0.25 points applied directly to their overall grade. So if you were at 89.75, that would bump you up to like 90. Okay. It's a little bit of extra work, so I like to provide a little bit of extra credit. So if at the end of Friday by midnight, if it's 18 of 35 students, response rate is 50%, every student in the class receives 0.5 points of extra credit. So whether a student participates or not, they still receive the benefit. Again, and I will send an email reminder out later today. So scale is from 1 to 5. Students should, of course, choose whatever best describes their experience in the class. But I always like to point out that 3, which is in the middle, is not neutral. 3 is similar to earning a 50% on your overall grade. 50% is not neutral. It's halfway between 0 and 100%, but 50% is not neutral. 50% is a failing grade. So in the same way, 3 is not neutral. That's all. Okay. And again, that being said, students should absolutely choose whatever reflects their experience in class. But provide feedback. I mean, it's helpful to us. It stays in our official files. It's looked at very seriously. Everybody, our department review committee looks at it. Department chairs look at it. The dean looks at it. Everybody looks at it. And then it forms part of our official employee report. Okay. So yes. Yes, I'm going to put it. So 7 and 8 is already added it to there. So it's already on there at the end of chapter 4. 6, I will just add it on there. Yeah. Okay. All right. Well, have a good day, good week. All the best for the rest of your finals. And I will see you all on either on Saturday or during finals week. All right.